projects. In this video, we are going to explain about the project, which is automated cardiovascular disease diagnosis using honey badger optimization with modified deep learning model. Introduction of the project. Cardiovascular disease stands as a leading cause of mortality, emphasizing the critical need for early diagnosis and risk prediction. The project addresses the significant loss of human lives due to the delayed CVT detection, highlighting the importance of preemptive strategies to mitigate this health crisis. The project recognizes the wealth of medical information available in electronic health records and aims to harness this data for the development of a decision support system. By utilizing patient data, artificial intelligence, and domain knowledge, the goal is to create a system that aids in healthcare professionals in timely and accurate CVT diagnosis. Conventional manual analysis of heart disease related information is acknowledged as time consuming and prone to misdiagnosis. The project underscores the drawbacks of traditional methods and emphasizes the need for more efficient and reliable approaches to handle the complexity of CVD detection. The project positions AI, specifically deep learning and machine learning, as a powerful solution to overcome the limitations of manual analysis. The focus is on developing a prediction model that analyzes extensive healthcare information to provide a more precise outcomes compared to traditional diagnostic methods. The project introduces an innovative approach which is automated cardiovascular disease diagnosis using honey badger optimization with modified deep learning, which is ACVD HBO MDL model. This model incorporates essential elements such as standard scaling for data pre-processing, honey badger optimization for feature selection, a deep learning modified neural network for classification, and Bayesian optimization for hyperparameter tuning. Objective of the project. The project focused on cardiovascular disease, which is the leading cause of death worldwide. The primary objective is to implement an automated cardiovascular disease diagnosis using honey badger optimization with modified deep learning model for precise and timely diagnostics, preventing potential harm to patients. Inspired by the potential of machine learning, the aim is to harness ML algorithms to extract patterns and hidden relationships with medical datasets. The overarching goal is to facilitate accurate and rapid diagnosis of CVD, leveraging the capabilities of ML to predict disease development. The goal is to overcome challenges in healthcare dataset analysis with the increasing complexity of healthcare datasets. The project acknowledges the challenge practitioners face in making accurate predictions and understanding feature relationships. The primary objective is to address this complexity by implementing a robust feature selection strategy, playing a pivotal role in optimizing the performance of ML algorithm. The objective is to develop the ACVD HBO MDL model, which is technique. This involves applying a standard for the data pre-processing, which is standard scaling for data pre-processing, and utilizing the honey badger optimization algorithm to elect an optimal subset of features. The overarching goal is to enhance the classification of CVD through these advanced techniques. A crucial objective of the project is to validate ACVD HBO MDL technique by conducting experiments on benchmark medical datasets. The aim is to assess the model's performance in real world scenarios, providing tangible results that demonstrate its potential for practical application in CVD diagnosis. To implement this project, we need software and hardware requirements. Coming to hardware requirements, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, backend framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. To implement this project, we have designed various steps in the flow of work. The first step is importing the packages. This step involves importing necessary libraries and packages that are required for the project. We have imported NumPy for numerical operations, Pandas for data manipulation, Keras for deep learning, Matplotlib and Seaborn for visualization, sklearn for machine learning, and other relevant tools. The next step is exploring the dataset. In this step, the project involves loading and exploring the heart disease dataset. Here we understand the structure, data type, and content of the dataset, which is crucial for subsequent analysis and model development. Data processing. This module focuses on preparing the dataset for analysis. It involves the dataset is converted into Pandas data frame, facilitating easy manipulation and analysis. Keras data frame. We convert the data into Keras data frame. Unnecessary or redundant columns are removed from the dataset, streamlining the data for model development. The next step is visualization using Seaborn and Matplotlib. Data visualization tools such as Seaborn and Matplotlib are employed to gain insights into the dataset. Visualizations include histograms, scatter plots, and other graphs to better understand the distribution and relationships within the data. Label encoding using label encoder. Categorical data is often encoded into numerical values using techniques like label encoding. This ensures that data is compatible with machine learning algorithms. The next step is feature selection. This step involves selecting the most relevant features from the dataset. The honey badger optimization algorithm is employed for feature selection, aiming to enhance models' performance by focusing on key variables. The honey badger optimization algorithm is inspired by the foraging behavior of honey badgers, known for their tenacity and resourcefulness in finding food. In the HBA algorithm, this tenacity is translated into a two-phase approach involving random exploration, which is digging, and the focused exploitation, which is honey mode, mirroring the honey badger's search for optimal solutions. This adaptive algorithm is applied to feature selection by guiding the search process, where the exploration phase explores potential feature subsets and the exploitation phase refines the selection based on the quality of the solution found, contributing to an effective and efficient feature subset. The next step is splitting the data into train and test. The dataset is divided into training and testing sets. The training set is used to train machine learning models while testing set is reserved for evaluating its performance on unseen data. Coming to building the model. Here, deep learning models architecture are defined based on considering the selected features and desired outcomes. Training the model. The model is trained using the training dataset. During training, the model learns the patterns and relationships in the data to make predictions. Flask framework with SQLite for sign up and sign in. Flask, a web framework for Python, is employed along SQLite for user authentication. This step involves setting up a web application that allows users to sign up and sign in. User gives input as feature values. User input their feature values relevant to cardiovascular disease prediction. The given input is pre-processed for prediction. The input provided by the user is pre-processed to ensure that it aligns with the format expected by the trained machine learning model. Trained model is used for prediction. The pre-processed input is fed into the trained machine learning model, which generates a prediction regarding the likelihood of cardiovascular disease based on the input features. Final outcome is displayed through frontend. The prediction outcome is presented to the user through the frontend of the application, completing the user interface loop and providing valuable information regarding the predicted health condition. Algorithms which are used in this project are RepTree. RepTree is short of Reduced Error Pruning Tree. It is a decision tree algorithm used for classification tasks. It constructs a decision tree by recursively splitting data based on attribute values, aiming to minimize classification errors. It employs reduced error pruning to optimize the tree structure. RepTree is utilized for its ability to handle classification tasks, providing a transparent and interpretable decision making process, which can be crucial in healthcare and diagnostics. The next algorithm is SVM, which is Support Vector Machine. It is a supervised learning algorithm used for classification and regression tasks. It aims to find a hyperplane that maximally separates data points of different classes in high dimensional space, facilitating effective classification. It is suitable for binary and multi-class classification tasks, making it valuable in predicting cardiovascular disease based on its ability to find optimal decision boundaries in complex datasets. The next algorithm is bagging algorithm. It is an ensemble learning technique where multiple instances of a base model, for example decision trees, are trained on random data sets which are subsets of the dataset with replacement. The final prediction is often a combination of the individual models. Bagging can enhance predictive accuracy and reduce overfitting. It is beneficial in creating a robust model by aggregating predictions from diverse models, potentially improving the overall performance of cardiovascular disease prediction. ANN, which is Artificial Neural Network. It is a machine learning model inspired by the structure and function of the human brain. It consists of interconnected nodes, which are neurons, organized in layers, including input, hidden, and output layers, allowing it to learn complex patterns and relationships. ANN is employed for its capability to capture intricate patterns in healthcare data, providing a powerful tool for predicting cardiovascular disease based on a diverse set of input features. J48. It is an algorithm for constructing decision trees and it is an open source implementation of C4.5 algorithm. It recursively splits data based on attribute values using information gain or Gini index to optimize the decision tree structure. J48 is suitable for classification tasks and it is used for its simplicity and interpretability in predicting cardiovascular disease, facilitating understanding and trust in the decision making process. The next algorithm is SC algorithm, which is spectral clustering algorithm. It is a technique used for clustering and partitioning data points based on the eigenvalues of a similarity matrix. It explores the spectral properties of the data to groups similar instances together. SU algorithm employed for clustering or grouping related patterns in healthcare data, potentially aiding in uncovering hidden structures or subtypes related to cardiovascular health. The next algorithm is HBOMDL, which is Honey Badger Optimization with Modified Deep Learning. It is a customized optimization algorithm that integrates tenacity and resourcefulness of honey badgers into deep learning models. It combines aspects of honey badger optimization with the modifications tailored for deep learning tasks. It is specifically designed to enhance the training and performance of deep learning models. It is used in the project to indicate a focus on efficiently tuning the parameters of deep learning models for accurate cardiovascular disease prediction. As an extension, we applied an ensemble method that combines the prediction of multiple individual models to produce a more robust and accurate final prediction. Also, as an extension, we built the front end using Flask framework for user testing with user authentication. We have evaluated this project using different evaluation metrics, which are accuracy, precision, recall, and F1 score. Here we have comparison graphs for all those metrics. This is accuracy comparison graph. Here on x-axis we have accuracy score for each algorithm and on y-axis we have algorithm names. Accuracy simply measures how often the classifier correctly predicts. We can define accuracy as the ratio of the number of correct predictions and the total number of predictions. This is precision comparison graph. Here on x-axis we have precision score for each algorithm and on y-axis we have algorithm names. It explains how many of the correctly predicted cases actually turn out to be positive. Precision is useful in the cases where false positives are higher concern than the false negatives. This is recall comparison graph. It explains how many of the actual positive cases we were able to predict correctly with our model. Recall is useful metric in the cases where false negative is of higher concern than false positive. This is F1 score comparison graph. It offers a balanced measure of model's performance by considering both false positives and false negatives, serving as the harmonic mean of precision and recall. The algorithm which performs well among all these metrics will be used for final prediction. To execute the project, first we need to open the code folder which contains source code files. This is the code folder of the project. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in HTML templates. This is the model file, which contains the algorithm information and that will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. This is the signup.db file. This file is the database file used to store the user information. Now to execute the project, we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. Here we can see that current directory is changed to the code folder's path. Here we need to type the command python space app.py and click on enter. This will compile app.py file and this will perform a runtime script for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port, unless configured differently. This is the local host and this is the port. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project which is displayed in the browser. And this web page is built by using the Flask framework. Here we can see a sign up link. First we need to click on that and enter all the sign up details if we are signing in newly. I have already signed in, I have an account in it, so we'll directly click on sign in. Here we need to provide our credentials which are the username and the password. So I'm giving my username and the password. Now we need to click on log. Here we can see the parameters which are need to be entered. These are the medical parameters of the patients which are need to be entered. Based on the given parameters, the system will predict whether the person is suffering from cardiovascular disease or not. Here we have sex. It represents the gender of the individual, which is a crucial factor in cardiovascular risk assessment. Here we have chest pain type. It describes the type of chest pain experienced during the assessment. Here we have resting BPS. BPS refers to blood pressure systolic. It indicates systolic blood pressure at rest, which is a key cardiovascular risk factor. Here we have rest ECG. Resting ECG, which is resting electrocardiographic results. It provides information on resting electrocardiographic results, aiding in the diagnosis of heart conditions. Here we have exercise angina. It is a binary parameter indicating the presence or absence of exercise-induced angina, which is a significant symptom in cardiovascular assessments. Here we have old peak. It measures ST segment depression during exercise, offering insights into the heart's response to physical activity. Here we have ST slope. It describes the slope of the ST segment during the exercise stress testing, providing information on the heart's response to the exercise. Now we understood all the parameters. Now we will enter them step by step. So here, gender is 1, which means the person is male. Chest pain type is 3. Resting BPS is 128. Rest ECG is 1. Exercise angina is 0. Old peak value is 3. ST slope is 1. Now we will click on predict. Based on the given parameters, the patient is diagnosed with heart disease, which means the person is suffering from heart disease. Now we will enter other person's details, which are parameters. So click on home. So the gender is 0, which means person is female. Chest pain type is 4. Resting BPS is 120. Rest ECG is 0. Exercise angina is 1. Old peak value is 0.6. ST slope is 1. Now we will click on predict. So here we got the prediction as the patient is diagnosed with heart disease, which means the person is not suffering from the heart disease. In this way, if we enter the medical parameters, which are the patient parameters to the system, then the system will predict whether the person is suffering from cardiovascular disease or not. Now we will sign out. Conclusion of the project. The project successfully introduced an automated cardiovascular disease diagnosis using honey badger optimization with modified deep learning model, combining advanced optimization techniques and deep learning for enhanced accuracy in cardiovascular disease prediction. Utilizing the honey badger optimization algorithm, the project demonstrated the significance of feature selection, ensuring that the most relevant parameters are considered for cardiovascular disease diagnosis, contributing to improved model efficiency. Employing a combination of data pre-processing techniques including standard scaling and label encoding, the project ensured that the medical data was appropriately formatted for model training, enhancing the robustness of ACVD HBO MDL technique. The inclusion of a variety of machine learning and optimization algorithms such as RepTree, SVM, bagging algorithm, ANN, J48, SC algorithm, and innovative HBOM DL reflects a comprehensive approach leveraging diverse methodologies for accurate and reliable cardiovascular disease prediction. The integration of the Flask framework with SQLite for sign up and sign in, coupled with a user-friendly interface for inputting feature values, demonstrates the project commitment to practical implementation, allowing users to interact with the model for personalized predictions and outcomes.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Project's YouTube channel and subscribe.